Welcome to NPTEL MOOCs course on Computer Vision and Image Processing, Fundamentals and Applications. In this class, I will briefly explain one important application of computer vision, that is video surveillance. There are many applications of automated video surveillance systems. So I will explain about all these applications. Also, there are many research problems in developing an automated video surveillance system, and mainly I will explain two important concepts. One is the background modeling and another one is motion estimation. In motion estimation, I will explain one important algorithm, that is optical flow. Let us see what are the important applications of a video surveillance system. So some of the important applications like access control in special areas, like in the airport, railway stations, maybe in the tunnels. So this is one important application, that is the access control in special areas, anomaly detection and alarming, and another one is the crowd flux statistics and congestion analysis. So these are some applications of an automated video surveillance system. So in the figure you can see I have shown one example, that is the anomaly detection and alarming. So here I am considering you can see the tracking, that is people tracking, and from this I want to detect anomalies, and accordingly we can give some alarms based on the anomalies. So this is anomaly detection and alarming. And here I have shown one practical example, that is the London bomb attack. Here in the figure you can see I have shown some of the frames of the CCTV video sequence, and in this case you can see the terrorists were detected by CCTV. So this is related to London bomb attack. So I have taken the pictures from this website, and this is one application, that is the anomaly detection. Next also I have shown some frames of a video sequence, that is from the CCTV, and this is nothing but the anomaly detection. And another application is the traffic information. So I can track cars, I can track vehicles, and accordingly I can get the traffic information. So this is also one important application. But there are problems for these automated video surveillance systems. The first problem is the temporal variation dynamic environment. So what is temporal variation? Suppose if I want to recognize activities, suppose the person is doing some activities, then in this case we have to consider the spatio-temporal variations, as I mentioned in the gesture recognition. In gesture recognition also we have to consider the spatio-temporal variation. In this case also, for human activity recognition or maybe the human action recognition, we have to consider spatio-temporal variations. And also, whenever I want to detect a person or maybe a particular object, we have to do the segmentation of the foreground from the background. But the problem is the background may be cluttered background, or maybe the illumination may changes, or maybe the background may be the dynamic background. Then in this case it is very difficult to do the background subtraction. For all these conditions, particularly the illumination variations, cluttered background, dynamic background, it is very difficult to do the segmentation of the foreground objects from the background. So that is the dynamic environment and also the temporal variation. The next point is the abrupt object or the camera motion. So there may be abrupt object or the camera motions. Then in this case also we have to do the tracking, we have to do the background subtraction. So all these things we have to do, but we have to consider these cases, that is the abrupt object or the camera motion. And also we can employ multiple cameras for a video surveillance system. So for multiple cameras, the field of view will increase as compared to single camera. But the problem is I have to find a correspondence between all these cameras, the multiple cameras. So that is one research problem. So how to find a correspondence between all these cameras available in the video surveillance system. Also we need all the outputs in the real time. So that is why one important issue is the computational complexity of the algorithm. So these are the main problems for an automated video surveillance system. So again I am showing some of the difficulties. In this case I am showing the concept of the tracking, but in the image you can see the people merged together. That means there may be some occlusion, and because of this occlusion it is very difficult to track. So here you can see the people merged together. In this case also the people merged together. In this case also we have to do the tracking, but it is a difficult situation. So in this case also we have to do the tracking. Next one is the people are occluded by a car, and that is also another example of the occlusion. So for a particular time maybe people are occluded by a car, then also we have to do the tracking. So this is one difficulty. And also if I consider the tracking of vehicles, then the problem will be the shadow. Even for the tracking of people, the problem may be the shadow. So the cast shadow, that means the shadow of the vehicle we have to consider. So vehicle will be moving at a particular speed and its shadow will be also moving. So in this case we have to do the segmentation of the vehicles from the background, and after this we have to do the tracking. So the tracking in presence of shadow is a big difficulty. So we have to do this, we have to remove the shadow, and that is also another research problem in video surveillance. So let us consider one generic framework of a video surveillance system. So input is the video. After this we have to detect the objects present in an image, and after this we can employ some machine learning algorithms, the pattern classification algorithms for object classification. After this we can do the tracking of the objects, and also we can employ this one, that is the action recognition we can do, that is the activity recognition. Suppose the people are walking or people are standing like this. So for this we can recognize different actions, that is similar to the gait recognition. Gait means the walking style. So that is we can do, that is action recognition. And output is the output video and the semantic description. So I will be getting the semantic description of the input video. So this is the generic framework of a video surveillance system. And you can see what is the difference between the object detection and the object tracking. So object detection means detect a particular object in an image. So here you can see I am detecting these objects, and that is nothing but the object detection. But what is the object tracking? To track an object or maybe the multiple objects over a sequence of images. That means the sequence of images means the frames of a video. So in this case I have to find the correspondence between the frames of a video. That is to track an object, maybe a single object or maybe the multiple objects over a sequence of frames of a video. That is the object tracking. And how to detect the object, that I am showing one simple flow chart here. So suppose the object is stationary. After this we are considering the image acquisition. After this we can detect object. So object detection algorithms are available. After this again the image acquisition from the video, that is the frames I am collecting or the frames I am taking from the video. And after this again I am doing the object tracking. And suppose the object is lost in a particular frame, then again we have to detect the objects. And if the object is not lost, then we can continue the tracking. So you can see first I have to detect the object present in an image or present in a video. After this we have to do the tracking. In some of the frames the objects may get lost. Then in this case again we have to acquire the frames of the video and we can detect the object, and after this we can continue the tracking. Like this we can do. But the object, if it is not lost, then we can continue tracking. So this is a simple flow chart to detect objects and also do the tracking. So here you can see I am showing one example, the detection of the moving objects. this person is moving, and we have to detect the moving objects based on some algorithms, but the problem is the shadow, that is the cast shadow we have to remove. The person is moving and his shadow is also moving, so that is why the problem is detecting the moving objects. So that is why we have to develop some algorithms so that we can remove the shadow. That is the problem of detecting the moving objects in presence of shadow. After this object classification, so we can consider the classification of objects present in an image or maybe the video. So here you can see we are classifying the objects, the car, the pedestrians. Like this we can do the classification based on some algorithms. That is also very important. So we can employ some machine learning algorithms for object classification. And the tracking, already I have explained, it is nothing but finding the correspondence between the frames of a video. In this case I have shown some of the frames of a video. So here you can see the 563, that is the frame number, 566, 567, like this, these are the frames. And you can see the person 1 is moving and person 2 is also moving, and there may be occlusion. In this case you can see in the image 567 there is a occlusion, and in presence of the occlusion also we have to track the person 1 and person 2, and you can see the output of this, the tracking algorithm. So we can track person 1 and the person 2 in this video. So tracking means the finding the correspondence between the frames of a video. So some of the traditional methods for all these activities, for moving object detection we can employ the background subtraction algorithm, and also we have to remove the shadow, that is the shadow removal algorithm we have to employ. For object classification simply we can employ the shape information, that is the shape based classification we can do. And for tracking of the objects we can employ the model based tracking and also the feature based tracking. In case of the model based tracking we can consider the model of the object, maybe the geometrical model we can consider, and based on this model we can do the tracking. In case of the feature based tracking we can consider some of the features, maybe the color feature, maybe the texture. So all these features we can consider, and based on these features we can do the tracking. So these are the traditional methods employed in the video surveillance system. And the major problems of the background estimation, so one is the random illumination variations that we need to consider. So illumination is not uniform. So if there is a random illumination variation, then the problem of the background subtraction, the background estimation. And the background may be cluttered and also the dynamic background. So in this image you can see the background is very cluttered, and one train is moving, that means the background is dynamic. And we want to track these persons. You can see I am doing the tracking in presence of the moving background and the cluttered background, and also the illumination is not constant, not uniform. Random illumination variations are available in these images in the video. And also we have to do the initialization of the moving objects. In this video or in these images or in these frames of the video you can see we have the moving objects. This person is moving, this person is moving. So we have the moving objects, and also some persons they are sitting here, that means they are stationary. So we have to initialize the moving objects. And also as explained earlier, so we have to consider the shadow problem. And one difficult problem is the removal of the cast shadow, because the shadow is also moving and the person is also moving. So based on the motion information I cannot do the separation between the moving objects and the shadow. So we have to employ some algorithms so that we can remove the cast shadow. Now I will discuss the concept of the background subtraction. So one very old algorithm is the temporal differencing. So this algorithm I can apply to detect foreground objects by making use of pixel wise differences between 2 or 3 consecutive frames of the video. That means I have to find the differences between 2 or 3 consecutive frames, and the pixels are marked as foreground if they satisfy the following equation. Suppose if I consider a particular pixel, the pixel at the time t plus 1 is I t plus 1 minus it, that is the pixel, that pixel at the time t. If the difference between these is greater than a particular threshold, then we can consider that pixel as a foreground pixel. Otherwise, it is a background pixel. Like this, we can determine the moving pixels. In this case, I am showing one example of foreground extraction, that is the background subtraction. That is nothing but the sense detection algorithm. So, this is the current image and I am considering the background image. If I subtract the background image from the current image, I will be getting the foreground pixels. So, this is nothing but the background subtraction algorithm. So, again I am showing the same thing, the background subtraction algorithm. So, this is frame 1, another one is the frame 10. So, if I do the subtraction, then I will be getting the difference of the two frames, that is nothing but the moving objects I can determine. And similarly, I am showing one example of the absolute differences. So, two frames I am considering. So, you can see in the first frame the moving objects are present. In the second frame the background, that is the nothing but the background. And if I subtract the second image from the first image, I will be getting the moving objects. That is the moving objects will be detected. That is nothing but the absolute differences. So, in this example, I have shown one algorithm, that is a simple algorithm for background subtraction. So, background subtraction system flowchart. So, suppose I have the input video and I am considering the frames of the video. First, I am considering the n frames, the first n number of frames I am considering, and based on this I am determining the background model. So, the background model is determined from the first n number of frames. After this, suppose one input frame is coming, that is the input current frame, and I can employ the background subtraction algorithm. So, you can see I have the background image here and I have the input current frame. So, I can employ the background subtraction algorithm, and based on this I can determine the foreground pixels and the background pixels I can determine based on the matching. And this based on the background pixels, I can update the background model that already I have developed from the first n number of frames. And also I have to consider the brightness sense removal. So, there may be changes of the brightness. So, that also we have to consider, and I will be getting the foreground. After this, we have to do some post processings. So, maybe we can employ the morphological image processing operations like the dilation, erosion, noise filter, like this we can employ, and ultimately I will be getting the output, that is nothing but the foreground image I will be getting. So, I can separate foreground and the background by considering this background subtraction algorithm. And this is also a very old technique. Here it is published here, that is IEEE transaction on pattern analysis and machine intelligence. So, briefly the concept is like this. So, the background is modeled by representing each pixel, the pixel is x, by three values. So, three values are considered. One is the maximum intensity value mx, one is the minimum intensity value nx, and the maximum intensity difference between the two consecutive training frames, that is the dx. So, by using these three values, one is the maximum intensity value, another one is the minimum intensity value, and another one is the maximum intensity difference between consecutive training frames, I can develop the background model. So, how to do this? So, pixel x from the current image I is considered as a foreground pixel if the following equations or the following equation is true. That means Ix, that is the current pixel, minus mx. What is mx? That is the maximum intensity value mx is greater than lambda dx, or maybe Ix minus nx. Nx is nothing but the minimum intensity value is greater than lambda dx. So, based on this I can determine the foreground pixels. So, briefly this is about the algorithm. So, based on this I can determine the foreground pixels, and this is also a very popular technique for background estimation, background modeling. So, we can employ single Gaussian model. So, in this case what we can consider, each pixel in the background reference follows a single and separate Gaussian distribution. So that means each pixel in the background follows a single and a separate Gaussian distribution. So that means for a particular pixel we can consider a Gaussian distribution, and which is characterized by the mean and the standard deviation. So that means each pixel in the background model consists of two parameters based on n number of background images. So we can consider n number of background images. So from n number of background images we can determine the mean and the standard deviation that we can determine, and that is nothing but the background model of the image. And suppose it be the value of the pixels in the image at the time t. So suppose I am considering the pixel at the time t. The pixel will be assigned or maybe the classified as a foreground pixel if it satisfies the following equation. So this equation should be satisfied. So it means the value of the pixels in the image at time t minus the mean is greater than lambda sigma t. If this condition is satisfied, then I can consider that particular pixel as a foreground pixel. So lambda is a user defined parameter, and I am considering the difference between the pixel and the mean that I am considering, it minus mu t. If it is greater than lambda sigma t, then we can consider that particular pixel as a foreground pixel. So lambda is a user defined parameter, and after this the parameters of the pixel I should be updated. Again we have to update the parameters corresponding to the pixel I. So the mean is updated like this, and also the variance I can update like this. So these are the updating equations, and in this case the alpha is a parameter, and that is used for the learning rate. So I can control the learning rate based on the value of the parameter alpha, and generally the value of alpha is 0.9. So this is the concept of the single Gaussian model. The next one is I can consider the mixture of Gaussian model, that is the mixture Gaussian model. So what is the concept of this? So each pixel in the background is modeled as a mixture of Gaussians. So I can consider the pixel as a mixture of Gaussian, because a single Gaussian model may not be appropriate in many cases. Suppose the background is moving or maybe the illumination is changing, then in this case the single Gaussian model may not be appropriate. So for this we can consider the mixture of Gaussians, and the probability of observing the current pixel value xt at the time t is given by this. So probability of xt is given by this, and here the k is the number of Gaussian distribution. So how many Gaussian distributions are employed to represent a particular pixel or maybe the background, and WIT is an estimate of the weight. So WIT is nothing but the weight, and you can see I am considering the ith Gaussian components. So xt is nothing but the pixel value, and I am considering the mean and the standard deviation. And after this we have to update the weights by using this equation, and here the beta is the user defined parameter, that is nothing but the learning rate, and MIT is 1 for the model which is maths and 0 for the remaining models, that is about the MIT. And this mean and the standard deviation or the mean and the variance should be updated like we did in the single Gaussian model. So this is the concept of the mixture of Gaussian model. So briefly I have explained this concept, the mixture of Gaussian model. And this is also a very popular method, the background modeling by codebook construction. So you can see this research paper by Kim. So this research paper you can see, and I think this is one of the popular method, but this is a very old method now. So in this case the codebook algorithms is employed, that is nothing but the codebook construction, and in this case the concept of the quantization or concept of the clustering is employed to construct a background model. So samples at each pixel are clustered into the set of code words. So each pixel, that means if I consider samples of the pixels from the training image, they are clustered into the set of code words, and the background is encoded on a pixel by pixel basis. So for each pixel I have the code word and the background is encoded on a pixel by pixel basis. A particular pixel can be classified as a background pixel if it satisfied the following two conditions. So first we have to consider the case of the color distortion. So based on the color distortion we can take a decision whether a particular pixel is a foreground pixel or the background pixel, and also we have to consider the brightness difference. So brightness lies within the brightness range of the code word, that also it is considered, and based on this we can select the foreground and the background pixels. So this is briefly the concept of the background modeling by codebook construction. For more details you can read this paper. So these are some results we have done, background modeling by the codebook technique. So corresponding to this image you can see I am extracting the foregrounds, and similarly to this image I am extracting the foregrounds. Very difficult images in the second image because the background is, you can see dynamic background is also there, and also illumination variations are also there, and the background is very complex. So these are some results of the background estimation, that is the foreground separation from the background. And one important technique is the Lucas-Candace technique, that is the concept of the optical flow. So we can determine the visual motion pattern of the moving objects, and that is called the optical flow. So here you can see this person is moving, and corresponding to this motion I can determine the visual motion pattern I can determine. That means I can determine the motion vectors. So here you can see these are the motion vectors, that is nothing but the optical flow. So based on the optical flow determination I can determine the moving objects, that is nothing but the motion estimation. So this algorithm I am going to explain, that is the motion estimation by optical flow. So what is optical flow? This concept is very important. So optical flow can describe how quickly and which direction the pixel is moving. So that means I am determining the motion pattern, that is the visual motion pattern can be determined by the optical flow algorithm, and we can determine the motion vectors, that is nothing but the flow vectors to detect moving regions. And the optical flow approach can be combined with other background subtraction methods. So by combining this optical flow method and the other background subtraction method we can determine the moving regions, that motion estimation we can do, and we can separate the foreground from the background. And I have to consider these assumptions. One is the optical flow should not depend on illumination changes in the scene. That means the illumination should be almost constant for optical flow determination. That is one assumption. The second assumption is the motion of the unwanted objects like shadow should not affect the optical flow. So that also we have to consider. That means we have to avoid, or we should not consider the unwanted objects, and if the shadow is present that will be a big problem for optical flow algorithm. So that we are not considering the presence of the shadow or the presence of the unwanted objects. So these two assumptions we are considering for determination of the optical flow. Now let us see how to determine the optical flow. Here you can see in this example I have shown this object is rotating. It is rotating like this in the counterclockwise direction, and corresponding to this I will be getting the optical flow, that is the motion pattern I will be getting. And ideally the optical flow is equal to motion field, because the object is also moving, and corresponding to this I will be getting the motion vectors, that is the motion field I will be getting, and also the optical flow I will be getting. But sometimes it may not be, the optical flow may not be equal to motion field. Here I am giving two examples. In the example A you can see this object is rotating, this is rotating, and I have the source, one source is available. So corresponding to this patch, suppose this patch I am considering, the illumination will be almost constant. That means if the illumination is constant, then corresponding to this there will not be any optical flow, because optical flow, how to determine? Optical flow is determined based on the illumination change, because the object is moving, and based on this the illumination at different points will be changing. But in this case the illumination at this particular point it will be almost constant. In the second case, there is no motion, you can see. The object is in stationary, that is the sphere is in the stationary, but I have the moving sources. The source is moving. So corresponding to this patch, suppose I have different brightness. The brightness will be changing. So whenever the brightness is changing, I will be getting the optical flow. But I will not be getting the motion because there is no motion field here. The motion field is 0. So in spite of having the motion is 0, the optical flow is present. So that means no motion field, but shading changes. That means the brightness corresponding to that particular patch, it will be changing because the sources are moving. So in the first case, motion field is there, but there is no optical flow. In the second case, motion field is not there, but there is a change of the brightness, and because of this I will be getting the optical flow. So that means I can say the optical flow is not equal to motion field. And the problem definition of the optical flow. So here I have shown two images, one is H, another one is I, and I have shown some pixels, the red pixels, the green pixels, like this I have shown, and the pixels are moving. So I have to determine the motion of the pixels, that is nothing but the motion estimation. So for this, you can see, find the pixel correspondence. So I have to find the correspondence between the pixels, and based on this I can determine the optical flow, I can determine the motions. So suppose this red pixel is corresponding to this red pixel, and similarly this pixel is corresponding to this pixel, like this. So I have to find the correspondence between the pixels. So for this I can consider some assumptions, like the color property I have to consider, or maybe the brightness property we can consider for the grayscale image, and also we have to consider this assumption, that is the small motion assumption we have to consider. Points do not move very far. So for this I have to find the correspondence between the pixels of the images. So the actual concept of the optical flow I will be explaining in the next slide. Here I have shown two frames of a video at time t, another one is time t plus delta t. And let us consider a patch at the point x, y. So this patch I am considering, and at the time t plus delta t, this patch moves to this position, the second position. So this patch will be moving, suppose. Now what will be the position of the patch in the second image? The position of the patch in the second image will be x plus u delta t, y plus v delta t. So in this case, what is x plus u delta t? U delta t is nothing but delta x. So that means it is nothing but delta x. And similarly the v delta t, it is nothing but the delta y. So what will be the position of the patch in the second frame? The position of the patch in the second frame will be x plus delta x, y plus delta y. And I am considering the velocity, that is the optical flow velocities, u and v. So u is the velocity along the x direction, and v is the velocity along the y direction. So from u and v I can determine the displacement. So delta x is nothing but u delta t, and delta y is nothing but v delta t, that I can determine. So assume that the brightness of a patch remains same in both the images. That is true here. You can see this patch is moving to this position, the second position. So that means the brightness of this patch will remain same in both the images. Only the position is changing, but the brightness of the patch remains the same in both the images. So here you can see that is the brightness at the point x, y at the time t. So E is the brightness of the patch at the point x, y, and at the time is t. And since the patch is moving to the another position in the time t plus delta t, that same patch is moving, so there will not be any brightness change. So corresponding to this, what will be the brightness? The brightness will be E x plus u delta t, because that is the new position, x plus delta x, y plus delta y. And what is the time? The time is t plus delta t. So brightness will remain same. So I can show another diagram. Suppose I am considering one object and it is rotating, suppose. So this object is rotating like this. So this is at time t and this is at t plus delta t. So if I consider the brightness at this point, suppose, will be same as that of this, because this point is moving and this is moving to this point. So brightness of this will be same as that of this. And if I consider the same position, so brightness at this position, the position number 1 and the position number, suppose the 2, the same position, it will be changing because of the rotation. So from this I can determine the optical flow. Here you can see corresponding to the position 1 at the time t and corresponding to the position 2 at the time t plus delta t, the brightness will be different because of the rotation. So based on this concept, I can determine the optical flow, because the brightness at the same point, because this point and this point is the same point, 1 and 2 is the same point. So brightness will be different because of the rotation. So that gives the optical flow. So now you can see the assumed brightness of the pets remains same in both the images, then I will be getting this equation. And this I can expand by considering the Taylor series expansion. So higher order terms I am neglecting, so I will be getting this one. So this equation I will be getting, and I can cancel out this and this will be cancelled out. So from this what I will be getting? So I will be getting this equation: delta x, delta E divided by delta x plus delta y into delta E divided by delta y plus delta t, delta E divided by delta t is equal to 0, and divide by delta t and takes the limit delta tends to 0. So from this I will be getting this equation. So I have to divide by delta t, so I will be getting this equation, and this equation can be represented like this. So I will be getting this one, the Ex u plus Ui v plus Et is equal to 0. So what is Ex? What is Ex in this case? Ex is nothing but delta E divided by delta x. That is the change of brightness with respect to the coordinate is x. That is the spatial change of the brightness. And similarly, if I consider Ey, that is nothing but delta E divided by delta y. This corresponds to the spatial change of the brightness because of the motion. And what is the dx dt? Dx dt is nothing but u, that is the velocity along the x direction. And what is the dy dt? So dy dt is nothing but velocity along the y direction, that is v. And what is delta E delta t? That is the time rate of change of brightness. The brightness is changing with respect to time, because already I have explained, suppose this object is moving like this at time t and at the time t plus delta t. So this is a t plus delta t. So you can see the brightness at this point. So brightness at this point, suppose 1 and 1, it will be changing. So change of the brightness with respect to time. So that is delta E divided by delta t. So I will be getting this equation. This is the equation of a straight line. So the velocity u and v must lie on a straight line, and based on this we can compute Ex, Ui and Et using the gradient operators. But the problem is, it is not a simple problem. U and v cannot be found uniquely with this constraint. So with this constraint I cannot determine the velocity u and v. So the same concept I am showing here. So this pets, it is moving to this position, and corresponding to this I will be getting the optical flow. The optical flow, it depends on the change of the brightness because of the motion. So already I have this equation. So this equation I can write like this. So what is the interpretation of this equation? You can see I will be getting this equation from this: minus Et is equal to, that is the delta E, that is the gradient of E dot C. So C is nothing but the velocity vector. So C is the velocity vector. So I have two components, one is the u, another one is the v, velocity along the x direction and the velocity along the y direction. And what is Et? Et means the time rate of change of brightness. So with respect to time, the brightness will be changing because of the motion. That is the time rate of change of brightness. And what is this delta E? Delta E is nothing but the spatial rate of change of brightness. So one is the velocity vector. So our objective is to determine the velocity vector from this equation. So this is the equation. This is the constraint equation or the optical flow equation. So from this equation, we can determine the velocity vector. The velocity vector is c. So I have two components, u and v. And for optical flow solution, there are many methods. So simply I am showing one method, but if you want to see the solution of this method, so you can see the optical flow paper, research paper by Horn. The original paper is by Horn. So you can see this research paper, the optical flow algorithm, you can see by Horn. But briefly I have explained the solution of this equation, and that is the optical flow equation. So for this we have to consider error in optical flow constraint. So this error I am considering, and also we have to consider another assumption, that is the velocity vector changes very slowly in a given neighborhood. That means the motion is very slow. So this assumption I have to consider, that is nothing but the smoothness constraint we have to consider, and based on this I am having this equation, that is nothing but the smoothness constraint. So already you have this equation, that is the optical flow equation, and this equation we can solve by considering the Lagrange's multiplier method. So E is equal to Es plus lambda Ec, that we can consider. So lambda is nothing but it is the Lagrange's multiplier, and based on this error, the flow error already we have calculated, because E is equal to Es plus lambda Ec, we have already defined Es and also we have defined Ec. The solution of this equation we are considering like this, we have to minimize the error and we will be getting this one. So we have to do some mathematics and I will be getting this one. And after this, the solution of this equation is nothing but I have to do the solutions, and finally I will be getting the velocity along the x direction, that is the u I can determine, and velocity along the y direction I have to determine. U bar is nothing but the mean velocity. These are the mean velocity, and m is defined like this, m and n is defined like this. So from these two equations I can determine u and v, that is the velocity vector I can determine. So I can show the simple algorithm from my book, optical flow algorithm. So initialize the velocity vector. First I have to initialize the velocity vector. After this I have to consider the iterations. So k number of iterations I am considering. So by using the previous equations, you can see I am calculating the value u and the v, and we have to stop these iterations. So first we have to consider this error. The error should be less than a particular threshold, and based on this we can stop the iterations. Otherwise I have to continue the iteration and I can determine the u and v. So this algorithm I can employ in a video. So in a video I have the frames, number of frames. So in that case the k is the frame numbers. So all the frames I have to read one by one, one number frame 1, number frame 2, like this. So k number of frames of a video I have to read, and from this I can determine the velocity along the x direction and velocity along the y direction. So briefly I have explained the concept of the optical flow, how to determine the optical flow. In this class I briefly explained the concept of a video surveillance system, and also I have shown different applications of a video surveillance system. The two main concepts I have briefly explained. One is the concept of the background modeling and another one is the concept of the motion estimation. For motion estimation I have explained the concept of optical flow, that is very important. In my next class I will be explaining some tracking algorithms for object tracking. So let me stop here today. Thank you.